Hi, my name is Akimi Takashi, just started as a project assistant professor at the University of Tokyo. And I'm presenting my postdoc work with Pedro Lopez and my co-authors at the University of Chicago. Today, we answer the question, okay. Today, we answer the question, can a smartwatch move the fingers? Here is my co-author Archit in a public cafe wearing a watch. But look, it looks as if the fingers are being controlled. His index finger goes up and the middle up and then thumbs up. But he is only wearing the smartwatch and nothing else. So the smartwatch is controlling his fingers. But how does it move them? Let me start with the current state of wearable devices. Wrist-worn devices, such as smartphones or fitness trackers, are the most popular wearable devices. Even commercial products have many sensors. For example, the Samsung Galaxy Watch 5 has motion sensors, skin impedance, motion monitors, heart rate sensors, location sensors, and so forth. Of course, in human-computer interaction research, there are many sensing approaches that are compatible with the size and feel of smartwatches. On the other hand, as output modalities, most watches have visuals, sound, and simple vibration. That's pretty much for most devices. Of course, soon we'll see tactile haptics joining these smartwatches, such as richer vibration, skin stretch, pressure, and so on. These will likely appear soon because their actuators are compatible with the size of smartwatches itself. But what if we try to add force feedback? Well, these cannot render the strong forces needed to move your fingers. So what actuators are strong enough for that? If you want strong forces to physically move your fingers or wrist, you need to employ bulky mechanical actuators such as exoskeletons, robotic arms, and pneumatics. However, these cannot be implemented in the size of smartwatches. As such, it is challenging to add strong force feedback to smartwatch. So, what can we do if we want force feedback with smartwatch? One of the potential methods is electrical muscle stimulation. Unlike the exoskeleton, electrical stimulation doesn't need mechanical actuator, only needs electrodes on the forearm. It uses small electrical impulses to create muscle contraction and actuate your fingers, so no big batteries are needed either. So it can minimize the size of the actuator. However, current electrical muscle stimulation requires users to roll up the sleeve, put electrodes all over the forearm, and calibrate them. This is hard because, look around you. We do not normally wear interactive devices in the forearm. So what if we could stimulate from a device that users already wear? For example, the smartwatch. When looking into the anatomical cross-section of the wrist, we found indeed some finger muscles and tendons pass in the wrist, so it could be possible to actuate the fingers. Let's try. Here, let's see how traditional electrical muscle stimulation have actuated the fingers. These two, the electrical stimulation electrodes, and then electrodes are put on the forearm with a certain distance. And see, the distance forces the electrical current to go deep into the muscle, so that moves my fingers. Like now, what if these two electrodes go through with the smaller distance apart? Like here's two small electrodes on the wrist, and when stimulate here, yeah, nothing happened. So then this small distance makes the electrical current too shallow to stimulate the muscle. So it doesn't move properly. So let's try something new. So let's switch to electrodes across the wrist. So I have also the electrodes here and here. And stimulate with this. Yeah. So you see now it works again. We found that this new way to stimulate the wrist forces the current deep into the wrist and moves some fingers. But how well does this work? That's what we found out in our first study, in which we stimulated the wrist and observed which finger movements resulted from this wrist-based stimulation. We stimulated their wrist with our device placed in 3 locations, determined by a preliminary study that found which places are acceptable for people to wear a watch. Then we varied the stimulation across all 12 electrodes and also had participants to hold their hands in 4 poses to understand different electrodes are more effective to actuate the fingers under different poses. This is the overview of the result of which joint is moved under all different conditions. This is a lot of data, so it is too hard to see, so let me show you the best we saw. The best result was when user wore our device about 4 centimeters from the top of the wrist, and we were able to robustly observe thumb extension, which creates a kind of thumb up gesture, index flex, which is probably the most useful for force feedback gesture, and the index extension, which is helpful feedback when pushing the VR, AR, or other mid-air buttons. Middle flexion, also useful for general force feedback. And the pinky flexion and the wrist flexion, which is very useful for force feedback too. Furthermore, we made a summary of which electrode generate which movement most reliable to accelerate future research on this. This is also a lot of data, so please check out our paper for more detail. So now we knew that electrical stimulation at the smartwatch location can move the fingers, so we implemented that prototype. We made 3D printed wristwatch band that has electrodes and all circuits inside. It has built-in spring that allows it to fit around the wrist. The PCBs comprise a power supply, control unit, and channel switching boards. The power supply board makes 3.3 volts from battery using a buck converter, 5 volts also from the battery using boost converter, and 100 volts from the 5 volt supply using a flyback converter. The control unit has 2 roles. One is to make current control pulses and to control the channel switching boards. The channel switching board is used to split the current control pulses to the 12 channels that connected to the electrodes. Okay, we found out that yes, a smartwatch can move the fingers, but is it practical? Turns out there's something like tricky I did not tell you about muscle stimulation. Here's a few of papers on muscle stimulation from last years. In 99.9% of all muscle stimulation work, researchers are the ones calibrating. But with our smartwatch, we wanted to try something new. What if we let the user calibrate themselves? This is what we found in our second study, which is also focused on how they feel when wearing our device in the public. We asked them to calibrate our wrist device and a more traditional forearm device that use the same style of electrodes too. We found the users were able to complete the calibration themselves, which is already a big win for interactive EMS. But more importantly, they were faster at calibrating the wrist device. Following that, without the participant realizing, my co-author Yudai, who conducted this study, asked the participants step out of the study room wearing our device. And I, a stranger to them, approached to them and greeting them, shook their hands and started talking to them. and later you then ask them to go to the cafe and buy something. Not that they were still wearing the device. So when they returned to the room, we asked them about their experience using this in public. All 8 participants reported no changes in their behavior while wearing the device. You can see our paper for many examples, but let me share just two quotes. It was a perfectly normal conversation. Having the watch on felt very normal. I barely even noticed having it on. It was a normal interaction in a usual way. I would order a drink at the cafe. Finally, all participants preferred wearing our device in the wrist than one in the forearm. Then let me show some application enabled by our practical form factor that you normally do not see in electrical muscle stimulation. The first is navigation app, in which our smartwatch that tells the user where to turn by stimulating their finger to point left or right, allowing eyes preparation. The next is exploring gesture-based notification during everyday activities. Here you see our watch creating a haptic notification that will user pace of the workout using the thumbs up, or even a gesture to indicate when to take a break. And finally, in this example, we see our watch assisting with a task where really we don't want a cable and the electrodes in a forearm. In this case, the user is learning drumming and uses our device to automatically pattern their left hand, while they practice by themselves their right hand pattern. So let me conclude. While we set out to add force feedback to smartwatch, we ended up also creating a practical form factor for electrical muscle stimulation. In fact, our participants found this to be more socially acceptable than existing muscle stimulation devices. We believe this points to new wave in which we will see more electrical stimulation in everyday device, all enabled by their form factor. For the future work, there's still a grant to cover for all of us here in this room, such as more precise stimulation, actuate more fingers, make it more robust across users, make it even more compact size, and improve it to calibrate even faster. Also, we have a demo tonight, so please come to try our demo. So lastly, I want to thank my co-authors and Sony for funding us. I'd like to hear your question. Thank you.
Thank you, Aki. Hi, I'm Jotaro from Sony. I would like to ask you one question about how you first introduced your project as a force feedback device. You introduced your project first at the force feedback device, and then I saw is most like I saw what you did is mostly like a gesture output, but I like if there's any feedback system that includes some touch or actual force feedback from some other for example virtual objects or something like that. If there's, have you thought of having actual feedback from the virtual objects using the device as an application?
What do you mean without EMS?
Yeah.
Actually, yeah. Actually, we searched for some studies to output the forces that one on a wrist. Actually, we couldn't find the devices that can move your finger without put some devices on a finger or some hand position, and then they have to put some like devices on the finger or hand. So there's no devices that can move your finger or wrist, only on the wrist. So can I answer your question?
I was mostly I wanted to ask if your gesture output, like you're flexing the finger on using the EMS, can be considered as a force feedback or a gesture output. Like, like for example, you could quantify the amount of force, like if you're like touching a virtual object, like have you actually tried to control the force rather than outputting?
Actually, I just found we can move the finger like goes up and then goes down, but we didn't like measure the how strong the force is. So, but yeah, but actually we made some like application in VR where we push the button on the VR.
Oh, so, okay, so you could also do the force feedback as well. Okay, thank you very much.
Thank you for the interesting presentation. I wanted to ask if you had any qualitative feedback on interference due to the gesture outputs, or did you do any sensing to detect when people are already moving their hand?
Actually, that's a good question. Actually, we want to like integrate sensing, like sensing and our device in the future, but actually we didn't like confirm if it interferes. So we have to check in the future.
Okay, thank you.
This will be our last question.
Hello, thank you for the great presentation. And I want to ask, you talked about the user calibration, and I want to hear more about that because you talked about like the acceptance of the public rather than this part. So I want to know whether it's that user can really program the activation or something. So yes.
Oh, actually, we made some program that with which the participant can calibrate themselves. So yeah, so they can calibrate themselves.
So they can program themselves that I want to do this motion when the
actually
program is
in the application the participants select which electrodes is stimulated and then increase or decrease the intensity of the electrodes and then find which electrodes is moved, which fingers.
Okay, thank you.
Thank you.